What is going on, guys? My name is Amos and I'm back again with another series of videos. So in this series of videos, we are going to be building an automata theory library in C. Now, of course, this is going to be, I've decided to call it autonLib. Now, let me just explain, the name. The first part, which is aut, comes from the, first part of the word automaton. And then the on, of course, is basically the last part of the word automaton, the same word, automaton. And then the lib here is just to mean that, of course, this is going to be a library, all right? So this library is going to be written in C, and why C? Well, it's because I want us to do everything from scratch. So we could have used another programming language like Java, for example, or maybe C++, or maybe any other object-oriented programming language, Python, JavaScript, or anything like that. But I want us to sort of like look at how we can do everything from scratch, how we can sort of like translate whatever it is, whatever logic it is that we want to implement, whatever feature it is that we want to add to this particular library. We sort of like want to do it from scratch and see how that the raw knowledge or the raw ideas translate into something that can be used, okay, something into code and into eventually something that can be used by other people to sort of like accomplish whatever it is that they want to accomplish. All right. So like I said, we're going to be building it from scratch, and then the goal is sort of like the first phase, we're going to like build like a basic CLI tool that everyone can use. Maybe later on we'll talk about how we can sort of like integrate a graphical user interface that can sort of like consume the features or anything that the features that our library is going to like offer and things like that. So we'll talk about that later on. But for now, we just focus on a basic CLI to basic interface, as long as the program is as long as the code is working and everything is good. So that is what we're going to be doing in this series of videos. Now, in case if you don't know what an automaton is, or if you like had a course on automata theory back in college or university or anything like that, and you maybe probably need a refresher or something like that, I've put up a few Wikipedia articles that are going to like help me explain that in briefly, and you can sort of like, I'm going to put these pages in links to these pages in the video description, so that you can read more about what I'm going to be about automata theory at your own time, right? So what is an automata? So here we have a basic definition of what an automata is, right? So, and where it comes from and things like that. Basically, go to this particular image that we're seeing here. So this is an example of an automata. So we'll basically have states, all right, states, and then these arrows that we see here, and of course the symbols we see on the arrows. So the arrows represent what are known as transitions, right? And then these circles are like states, right? These circles with letters S1 and S2 here are states of the automata. And then this arrow that depicted as if to like enter into some state S1 is there to represent that, it is there to show that this S1 is a starting state, right? And then we see that this is a single circle. S2 here is enclosed in a single circle, but then S1 is enclosed in two circles. So this notation here is the double circles here mean that S1 is a final or accepting state. And then S2 here is there's no arrow, there's no ingoing arrow, there's no ingoing arrow. So this is not a starting state, and this is obviously a single circle, and so this is neither this is not an accepting state. So it is neither a starting state or an initial state, nor an accepting state, right? So this is just a state in the automata. And so you can look at the definition. They talk about things. You see terms like a language. So first of all, we have to start with the alphabet. If you look at the English language, for example, we have like an alphabet. So an alphabet is like a collection, or is like a collection of symbols that that language is going to recognize, for example. So if you look at the English alphabet, for example, we have letters from A to Z. So that is a collection of symbols that we can use later on to construct words, all right? So to construct words. And of course, a set of words is what is going to give us a collection of different words that can be constructed from this collection of symbols is what is known as a language, right? A language. So for example, in English, in the English language, for example, if the word they, for example, the word the, for example, the. So that is a word. And if you examine that word, you see that it's going to be a collection of symbols that are going to be recognized as being part of, the English language or something like that. So that is what a language is. So an automata is basically going to help us. It's basically a machine that is going to help us to identify words that a language can that a language accepts. So we'll have a bunch of words, we'll throw a bunch of words at this particular automata, and then this automata would tell us whether the word is going to be uh, whether the word is going to be accepted by some language or not. So this automata that we see here is accepting a particular language. So if we look at what we have here, the symbols here we have two symbols here. So let's take it that the alphabet for this language this automata is describing, we have two symbols, right? We have two symbols. We have 0 and 1. So words that can be formed from these two symbols of this particular alphabet are words like 0 1, 0 1 1, 0 2 2, or anything like that. Let me just maybe try to scroll down and see if there's anything. Oh, there's nothing. Great. So strings like 0 0, 0 1 like examples of combinations of symbols that are going to that we can understand as being words of some particular language. But then this is not like accepting all the possible combinations of zeros and ones that we can think of, or all the possible combinations of zeros and ones we can construct. It's basically accepting a subset. Or it's possible to construct a machine that is going to accept any possible combination of these strings of these symbols 0 and 1, but this is basically accepting a particular language, right? So it's accepting a certain combination, right? For example, 0 0, the string 0 0 is accepted because if I start from S1 and read 0, for example, I'll go to S2. I read another 0, I'm going to go back to S1, and then S1 is an accepting state. So if we end in an accepting state after reading a particular symbol, then that particular symbol is going to be accepted by the language. So this is what an automaton is, right? And of course, we have what our library is going to be able to do is that we'll first of all consider a subset of the entire theory, the entire automata theory. So we'll focus on regular languages, right? What is a regular language? Well, a regular language is a language that can be compressed into what is known as a regular expression. And what is a regular expression? A regular expression is something like this here. Do we have any examples of regular expressions? Now, I know that all this might sound, a bit, confusing and all that. If you've not, if you've not, had a course on maybe automata theory or anything like that. But don't worry. This is just, me setting the stage and trying to sort of get us up to speed and sort of see what we are going to be talking about. A regular expression is, now, how we have, these email addresses and so it basically, the email address has a particular format. For example, it has some part here, and then it has the first part, and then we read the first part, and we also have the @ symbol or something like that. So anything that is not going to have the @ symbol, for example, will not be considered as a valid email address or something like that. So we basically have a format that we are respecting. So the behind, if you are trying to fill out, to fill in, some particular form online or on some website, you basically, if you have a field for entering your email address or anything like that, you see that if you leave out the @ symbol or anything like that, you see that the email address is not going to be considered as a valid one. So you have to like enter a valid email address. So behind the scenes, we have a regular expression that defines the format that an email address that a valid email address is supposed to respect, right? So here, I think I saw a few examples, but I don't know where where to find these examples or something. So we can basically you can basically Google and you should see what a regular expression is. So a language that can be compressed into a regular expression, okay, a language that can be like converted into a regular expression that I can then say that, okay, every possible word I can sort of like come up with, every word I can construct is compressed into this regular expression. So that is going to be a regular language, right? So we have all this jargon and all this theory. So you can, I'll put these links to these pages in the description, so you guys can like reference this a little later at your own time and read more about what an automata is, or what an automaton is. If you don't know what, if this is your first time hearing the word automaton, or hearing the phrase, or hearing the combination automaton theory or automata theory, right? So our library will sort of like handle types of automata. So we have types. Now this is maybe useful. Let's quickly go through what the different types of automata that we have. Now the first type is going to be deterministic. So what does it mean? It's first of all finite. It's finite in the sense that we have a finite number of states. So here we have 3, for example. We might have 10. We might even have more states or anything like that, and all that is going to be taken care of, right? As long as we have a finite number of states. So we don't have an infinite number of states, right? We have n states, right? So here we have 3 states, for example, here. So this is deterministic. That's the meaning of the word finite. Now the word deterministic here means, if you sort of like examine this, let me maybe just zoom in. Let me just zoom in like so. So if you examine this example that we have here, you basically see that for every outgoing state, if we consider S0, for example, if we consider S0, for every outgoing transition, now a transition, remember, is represented by this arrow that we have here, and of course a symbol of the alphabet of a particular language, all right, of a particular language. Here the alphabet is 0, 1. Let's say, okay, we suppose that the alphabet is 0, 1 here. So if you look at S0, for example, and we examine all the outgoing transitions, you see that for every outgoing transition, we have a unique symbol that we are reading, or a unique symbol that we are taking into consideration. So we don't have like from S0 here, we have like 2 transitions with the symbol 1 that are going out of the state S0. So we don't have that here. So we have, for every outgoing transition, we have a unique symbol, right? A different symbol of the alphabet. So for example, S0, we have 1 here, we have 0. We are not seeing anything, maybe we're not seeing any other outgoing transition with 1 maybe going to a different state, let's say S2. So every transition goes to exactly 1 state on a particular symbol. So that is the meaning of the word deterministic. So we need, we'll sort of like treat this type, okay, and this is like the formal definition. You can like look at it at your own free time. So you see that we have here we have a transition table and any whatever it is, okay, we have a transition table. It's a transition table, sorry. And then we also have a non-deterministic version. It's finite, again, because we have a finite number of states. It's non-deterministic because it violates the whatever we saw, whatever it is that I explained about the deterministic version having for every outgoing transition, if we look at every state, and for every outgoing transition we have a unique symbol going to some another transition. So it basically violates that, right? So if you look at this example here that they are showing here, we see that if you look at the state P here, we have 1 outgoing transition with the symbol 1 going to Q. Again, we have another outgoing transition with 1 that goes to P. So we see that for the same symbol from P, we go to different states. So this is non-deterministic. So anyways, this is just a simple introduction. This is just an introduction of what it is that we are going to represent in memory. And probably in the next video, we'll look at how we can sort of like come up with a structure that is sort of like going to help us represent, to compress or to represent all this information that we are seeing here, in memory and something like that. All right, so we'll look at that in the next video, and how we can sort of like represent the alphabet and the different parts of this particular machine that we are talking about. So it's really a machine in the sense that it's it's a machine because it fits the definition of what a machine is. All right, and it's not like your normal mechanical machine or automatic machine or any automatic. Yes, it is automatic, right? So if you look at like the origin of the word itself, where it's coming from here, you can read more about the origin. You'll see you basically like read like where it's coming from and what exactly this is going to mean. So we'll like come up with a library. We'll write the library from scratch in C. And we want to handle basic operations we can perform on like automata. So we have a concatenation, we have the clean star, we have many other operations we can perform on such on such things. And of course, it's going to be very interesting. Now, this is I think that's all for this particular introductory video, and I'll see you in the next video where we're talking about how we can sort of like represent this automata in memory, and we'll start with the coding part. And of course, before starting in every session, we'll sort of like have a theory part where we explain what it is that we want to achieve. We give the theory and we give all the logic, and we'll then go to the finally transition to like implementing our logic in C. Right? Thank you guys for watching, and I'll see you in the next video.